ああ、そっか。おはようございます。
おはようございます。聞こえますでしょうか？
聞こえます、聞こえます。
はいはい。
僕はでもビデオはオンにできないんですね。
いや、できるはずです。パネリストにしたので。
ホストによってなんとかって言われ。
あれ？そっかそっか。ここなんか、それ、アローパネリストスタートビデオで、はい。設定しました。これでどうでしょう？
出ます。
できました。はい。今日はよろしくお願いします。
おはようございます。よろしくお願いします。
Hello. Good
Hello?
afternoon, Clark. And
Can you hear me?
Giacomo. Yes.
Great.
Thank you for joining us.
Sure.
Hi.
Hi.
Hello.
Hi. I am Hiroshi Maruyama, one of the panelists today.
Hello.
Great. Nice to meet you.
Nice to meet you. Giacomo, welcome. Thank you for joining.
Thank you.
Happy to be here.
Yeah, we are glad. And Professor Barrett, could you test to share your screen?
Yes, let's do that. Oh, it says you've disabled screen sharing for me.
Oh,
so
yeah.
You have to enable it.
Enable. Okay, I need view active lock webinar mute allowed. I switch on to allow the share of panelist PC. So could you try it again?
Yes. Okay. That looks like that worked.
Yeah, I can see. Thank you.
Okay. All right. Good. Let me try one more thing here. Need to share sound as well. Okay, let me just skip to a video and make sure you can hear it.
Mm-hmm.
Hello, my name is Michael Kokenderfer.
Yeah, I can.
Okay. All right, good. I think we're all set.
You. And first of all, I will present our workshop outline as an opening very shortly, and then I introduce Professor Clark Barrett for your keynote.
Sounds good. Is this the beginning of the workshop, or has there already been some events?
Or it's
No, this is the very beginning of the workshop.
Yeah.
Okay. Good. So you're all set?
Yeah.
I think so. We start at 8 a.m. in the morning and end at the midnight today.
Okay. Wow. That's intense.
Well, actually, during the daytime, we don't have anything, in between.
Okay.
Should I test screen sharing as well?
Yes, please.
Okay, let's see. Okay.
Yeah.
I think that works.
Yeah, I can see it. Good.
Okay, perfect.
So in Japan, the situation of COVID-19 is getting worse. We have the third wave of infection, and government is asking the people to stay, at least avoid the meetings and drinkings, and try to stay home. I don't know for the rest of the world, but
It's the same thing here. Yeah.
okay, I see.
Yeah, I mean, I'm in Montreal right now. We're not quite locked down. I mean, schools remain open, but by and large, things are pretty sequestered. So, restaurants for that matter are only open for takeout, for example. Those places of work are either open for a shoestring staff, but people aren't going in and moving about in the way that they normally might, or in the way that they were maybe tail end of the summer, let's say July,
Yeah.
August.
Yeah.
There's a strong seasonality component.
Yeah.
Right.
I think Futse is joining, but still connecting to audio, it looks like.
Yeah, I don't know what happens. Usually it doesn't take this long.
Yeah, so it's connecting to audio, but
Yeah. This can sometimes happen if the person doesn't realize they have to click some extra buttons to connect to audio.
Oh, I see.
Hello, Hood.
Hello.
Oh, good to hear you.
Yeah.
Hello.
Hello.
Nice to see you again.
Nice to
Hello.
meet you again. Long time.
Long
Hello,
time no see.
Yeah. Hello, Clark.
Hi, nice to meet you.
Nice to meet you. How are you doing? COVID is terrifying here.
It's bad everywhere.
Yeah. But it seems like Japan is doing a bit better, right?
Well,
Not really.
getting worse now.
Oh, really?
But compared to the US, I think it's much better. We have about 2,000 people every day as a new, the positive cases.
Oh my goodness.
That's
we have like 100,000 people every day.
Yeah. Well, I think US case is a bit special, I think.
Yeah. The California Bay Area, fortunately, is not as bad as many other places, so we're lucky that way.
Yeah. I don't know what the picture will be after the Thanksgiving week, right? Like, it's poised to be, I don't know, much more terrifying, probably.
Yeah.
Okay, attendees are coming, but shall we start our workshop? Hello, everyone. Welcome to iMLSE 2020, a second international workshop on machine learning system engineering. Before our keynote, I'd like to a little bit introduce our workshop very briefly. And this is the second series of workshop. First one were held in 2018, 2 years ago, including keynote of Professor Chan Jin-Tao of Kyushu University in Nara Prefecture in Japan. And this is the second one, including 2 research papers, 2 demonstration talk, and this 3 position talk besides our keynote talk by Professor Clark Barrett of Stanford University, and invited talk of Giacomo Cobo, Quantum Black, and panel discussion, ML 2.0, new faster, cheaper path to build machine learning systems. And we are about to start first session of keynote invite talk and panel discussion. Firstly, Professor Clark Barrett deliver a keynote, and then Giacomo deliver his talk about ML 2.0 and the panel discussion chaired by Hoots. And there are 2 sessions. A second session is for research talks, and poster session started at 1 p.m. UTC, including 6 talks. So, and lastly, I'd like to thank all co-organizers, steering committee, and program committees to hold this workshop. Okay, let us start at the keynote talk. Professor Clark Barrett of Stanford University. Clark Barrett is an associate professor of computer science of Stanford University, and his talk is about toward readiness verification for safe artificial intelligence. Would you like to start your keynote, Clark?
Sure. Let me go get started here. Okay, you see my screen?
Yes.
All right, great. Okay, so to start with, I'm going to remind you of some horror stories. Back in the 80s, there was this medical machine called the Therac 25, and it could do both radiation and X-rays. And between 1985 and 87, there were 6 times where someone received radiation when they were supposed to receive an X-ray, and they got a really bad overdose. In 1996, there was a famous example of a Ariane 5 rocket, which exploded shortly after liftoff. And the value of the rocket and cargo were estimated at least 500 million. And then back in 2003, when I was living in New York City, there was the largest blackout in the U.S., the history of the U.S., where the entire northeast of the United States had a power outage, and the estimated cost to New York City alone was over $1 billion. So what do these horror stories have in common? Well, they're all caused by software bugs. So it turns out there was a bug in the controlling software for this Therac 25 machine, so that if you hit a certain sequence of keys, there was a plate that was supposed to come down to turn the radiation machine into an X-ray machine, and the plate did not come down because of a bug in the software. The Ariane 5 explosion, embarrassingly, was the result of an unsafe conversion from floating point to integer in the software system. And the blackout was actually at least partly due to the fact that an alarm system that was supposed to alert First Energy in Akron, Ohio, had a bug in it. And so what was happening is it was filling up the logs with error messages so fast that it rebooted the machine, and none of the error messages ever made it to the monitors, so nobody ever saw those error messages. Okay, so well, I could tell you, and I'm sure you could tell me, lots of stories about software bugs and how bad they can be. So now what about AI systems? Well, AI systems in some ways are even worse. So we've learned a lot about how to do good software engineering. And often when there's a bad bug, it's because somebody didn't follow best practices, not because the best practices failed. But now with AI components, we have even more challenges. Consider, for example, AI components built with deep neural networks. So many of the traditional software engineering techniques like code reviews, code coverage, programming with assertions, modular programming, they're just not applicable to these kinds of systems. In fact, neural networks are such complicated artifacts that humans really don't understand what's happening. So we can sort of observe what's happening at the interfaces, but we don't have a good intuition for the actual function that's being computed. So how do we ensure that these systems are safe and correct, especially if they're going to be used in safety or mission critical applications? And that's sort of the big question. I don't have all the answers, but it's the big question I want to ask and talk about today. So to start with, I'd like to introduce the Stanford Center for AI Safety. And the mission statement is to develop rigorous techniques for building safe and trustworthy AI systems and establish confidence in their behavior and robustness, facilitating their successful adoption into society. So that's our mission statement. It's very lofty, but we think that it's an important goal, and that there are a lot of things we can do along this pathway. And the faculty directors of the center are myself, Michael Kokendorfer, and Dorsa Sadiq. And with their permission, I'm going to play a couple of videos about some of the work going on in their labs, and then I will tell you about some of the work that I'm doing. So that's the basic overview of the presentation today. And just to kind of give you a flavor for what are the things that the center is interested in. So we're interested in using formal methods for AI safety, including specification, verification, and verifying whether something is robust against adversarial attacks. We're interested in learning and control for AI safety. So how do you do safe learning, safe exploration, safe planning, things like that. And then also things like transparency, so fairness, explainability, and diagnosis and repair. Okay, so I'm going to start with some of Michael's work. And of course, Michael does a lot of work. He's a professor of aeronautics and astronautics, and also by courtesy computer science. He has expertise in collision avoidance for aircraft, as well as lots of different interesting AI techniques. And he's going to, in this video, he'll give a brief overview of sort of the high level things that their lab is working on, and then one of his students will talk about a specific project about AI safety for autonomous vehicles.
Hello, my name is Michael Kokendorfer. I'm one of the co-directors of the Stanford Center for AI Safety, and we'll be providing an overview of some of the projects we have been working on over the past few months. In our lab, we work on the mathematical models and algorithms for decision-making under uncertainty for safety-critical systems. We're interested in modeling, planning, and verification. Modeling involves going from data, such as aviation radar data, or LiDAR data from an autonomous car, to some kind of probabilistic model. In some cases, there may be inadequate data, and so we sometimes need to incorporate human expert judgment into the construction of our models. These models may range from Bayesian networks to generative adversarial neural networks. Planning involves taking these models to derive a plan. In problems where there is uncertainty, we generally want the plans to be reactive to how the environment evolves and robust to perceptual uncertainty. Validation involves going from this plan to some degree of trust that the system will behave as we intended when deployed in the real world. We'll be highlighting some research that we have done these past few months in these three areas of modeling, planning, and validation. My PhD student, Anthony Corso, will describe some of the research we have been working on involving automotive safety validation with adaptive stress testing.
So one of the major problems in autonomous driving is how do we validate the safety of these systems before deploying them on the road? Errors in perception, planning, and control can cause complex failures that may have been difficult to anticipate. So while traditional testing techniques are surely needed, we may also need automated and adversarial testing techniques. But adversarial testing techniques come with their own set of challenges. Number one is that they might find unrealistic scenarios. So consider this situation where a vehicle is driving down the road and encounters a pedestrian that's trying to cross. Our technique, adaptive stress testing, found a failure mode where the pedestrian decides to run headlong into the vehicle, which is coming to a safe stop. So I think we can all agree that this failure mode is probably not first in our list of things that we want to actually solve. The other problem that automated testing suffers from is scalability. So there are a vast number of possible driving scenarios that our autonomous vehicle can encounter. And even in a single class of scenarios, so for example, in this intersection scenario where the ego vehicle in blue is trying to take a left turn, there may be as many as 10 to the 13 different configurations of 5 vehicles on the road. So it's going to be totally intractable to enumerate all of the possible configurations of a given scenario. So to overcome these challenges, we first have to frame our problem as a Markov decision process so that we can solve it with reinforcement learning. So this is really the heart of our technique, adaptive stress testing. We have a simulator that contains within it an environment that the vehicle is going to be driving in, and the environment can contain things like other agents on the road, as well as sensor noise and other perturbations that could affect the behavior of the driving agent. And then we have the system under test, which is the ego vehicle that we're trying to stress test. Outside of the simulator, we have a reinforcement learning algorithm that's able to perturb the environment through an action and observe a reward. Now, we designed this reward function so that the rewards are high when we get situations where the system under test does something unexpected or has some sort of failure. So the reinforcement learning algorithm is trying to find situations that are challenging for the driving agent. So to address the first problem of finding unrealistic scenarios, we can take our reward definition and alter it so that it incorporates something known as responsibility sensitive safety, or RSS. So RSS is basically a set of common sense driving principles, such as don't rear end someone and right of way is given, not taken. And it turns those into formal mathematical statements about which actions are acceptable at a given time step. So what we can do is look at the actions of our system under test and see whether or not they are appropriate according to the RSS rules. If they are not appropriate, then we can be rest assured that something is wrong with the policy that we're running on the system under test, and we'll have found a failure that is actually relevant rather than one that is somewhat contrived, like the example I previously showed. Then the last challenge that we have is scalability. So to address scalability, we've taken the approach of decomposing the scene into a bunch of subproblems that are all in of themselves tractable. So what we can do is pair off each other agent on the road with the ego vehicle and then find failures for that smaller problem. Then we can go back and combine all of these subproblems together and fuse their results in a way that allows us to find failures of the more complex scenario. Okay, so to look at some results, if we apply our RSS metric into the reward function, we now find a very different failure mode in that same scenario that I showed previously. In this case, the adaptive stress testing algorithm finds a mode in which sensor noise tricks the ego vehicle into thinking that the pedestrian is still on the crosswalk or on the sidewalk, but when in fact the pedestrian has entered into the road, causing a collision. So this failure is much more relevant and is something that we'd like to work out before we deploy that vehicle on the road. The next shows results from our scene decomposition approach, where we are able to find failures in this complex 5-car environment using failures found in the 2-vehicle interaction for each of these 4 other agents on the road. And we can actually use this technique to generate a lot of failures and therefore get statistics about how likely it is that our ego vehicle fails. And so this plot shows our estimate of the probability of failure of that ego vehicle versus the number of samples required. And we see that our approach in purple is able to get an accurate estimate of the probability of failure in just about 10 samples, while the other techniques require almost 1,000 samples or don't get a good estimate at all. So with that, I'm going to conclude with 3 points. The first is that we can perform automated testing using adaptive stress testing on automated vehicles to find complex failure modes. But we need to incorporate some common sense driving principles in order to guide the search towards important failures. And lastly, we can use scene decomposition techniques to solve the safety validation problem in complex driving scenarios.
To conclude this presentation, I would like to point you to some additional resources. So the first is a survey of algorithms for black box safety validation. This survey was led by Anthony Corso, and it encompasses many of the emerging research directions. We have also been involved in the building of a number of driver models using generative adversarial imitation learning. And a synthesis of the work that we have done along these lines. We have also done a survey on driver models in general, and we have posted this survey on arXiv. It took about 2 years to write. I'm also really excited about a preprint becoming available of a new book titled Algorithms for Decision Making, where we talk about POMDPs and Markov decision processes, Bayesian networks, as well as validation. If you're interested in receiving a PDF copy when it becomes available, you can register your interest on algorithmsbook.com.
Okay, so that is Michael and his lab. So I'd like to thank him for preparing this video.
Hello, my name.
All right, so now we're going to go and hear a little bit from Dorsa, the other co-director of the Center for AI Safety. And Dorsa's work, she does a lot of different work, but the work she'll be talking about is primarily in interactions between autonomous systems and humans, or more specifically between robots and humans. And there's an important safety component, obviously, whenever you have an autonomous system interacting with a human. And Dorsa's work does look at some of those safety concerns, but I think a lot of the work she'll talk about is even more fundamental. How do you even think about these kinds of interactions between humans and robots? How do you model them? How do you get the robots to learn from the humans to interact with the robots? So she'll give you a brief overview of some of the things in that direction.
All right. So hi, everyone. So today what I'd like to talk about is two main categories of work that we have been working on this past year. One is around learning human preferences, where the human is this teacher with many sources of data and the robot is just trying to learn from the human. And the second perspective is more of an interaction perspective, where the human and robot are symmetric agents in a dyadic setting. They're trying to do a collaboration together. So let's just get into it. When we think about learning human preferences, we might be thinking about learning a reward function or learning a policy. And we usually do that based on having access to expert demonstrations. Imitation learning from expert demonstrations has been around for more than 2 decades now. But we have been looking at a few set of other directions where we don't assume that we only have access to expert data, but we assume that we can have access to a lot of different variety of data and tap into these different sources. So first, we've been looking at this idea of learning from suboptimal demonstrations. So we have access to both expert data as well as data from different dynamics, the robot with different dynamics or suboptimal data. And based on these demonstrations, we have a notion of optimality and feasibility. And based on that, we score the trajectories and we do imitation learning. We've also been looking at other sources of data. For example, what can we learn from language instructions? So Sid has been working on this problem where we can interactively teach a robot how to do a task. For example, when a person comes in and says, wash the mug, can the robot interactively learn from that? And how can we do that based on decompositions? So if a person comes and decomposes that task, how do we use these decompositions together in order to figure out what is washing the mug and what is not washing the mug? And then based on that, how do we update our model in an online fashion? So if the robot comes and says, wash the mug again, we would be able to do that. Moving forward, there are also other types of data, for example, pairwise comparisons, rankings, or ordinal data that we can rely on. And Erdem has been looking at this idea of active preference-based learning based on these types of queries, pairwise queries, where we show two different trajectories, A and B, and then we ask a user what your preferences are. And based on that, we're trying to learn an underlying reward function. The thing is, if this reward function is linear in a set of features, it's not able to capture a variety of tasks. In this case, it's not really going to be able to capture these different targets that the robot is trying to push the golf ball into. So what we've been looking at is using Gaussian processes here and doing active preference-based learning over Gaussian processes. The detail of this is in this RSS paper, but I just want to show you how this works in practice. So if you use a linear reward, the robot only targets the sites. But if you use a Gaussian process reward, we are able to capture any of these targets that we have down the line here. Finally, another type of data that we can have access to is physical correction. So a robot is not really an AI agent, right? It has an embodiment. So because of that, we can actually move it around. And what Mangshi has been looking at is when we have multiple robots coordinating with each other, trying to do a task incorrectly. For example, let's say they're trying to help us unpack these groceries, but not based on humans' preferences. How can the human provide feedback and a sequence of physical feedbacks? And the fact that how can we learn from these sequence of physical feedbacks and interdependencies between them in order to better learn a reward function or human preferences. Moving forward, another idea that we have been thinking about under interaction is how to capture risk-aware human models, specifically how humans act in near accident scenarios or when there is some notion of risk. The idea is so far I've been talking about learning reward functions, and I've been assuming that humans follow some sort of optimal action or they're rational. Maybe like in best case scenario, they're noisily rational. But the thing is, this still doesn't capture the fact that sometimes the most likely action of the human is something that is suboptimal. So what we've been looking at is developing risk-aware models based on ideas from prospect theory that captures this risk awareness and this type of suboptimalities of humans. So Manet has been experimenting with this on various types of tasks like autonomous driving as well as block stacking, where a robot correctly detects human suboptimalities and coordinates well here. Another idea we've been looking at under interaction is this idea of learned representations and the fact that they can help us for better coordination. Dylan has been working on this idea of learning latent actions for the setting of assistive teleoperation, where we have a set of demonstrations from an expert or a caregiver. And based on that, we are learning this latent representation, latent low-dimensional action in order to be able to do various sorts of assistive teleoperation tasks. Dylan has also looked at integrating this with shared autonomy in order to do more precise tasks like picking up food or looking at feeding at the moment. This idea of representation is also pretty powerful when it comes to coordination with other agents. We've been looking at that for this various settings like coordination and influencing between humans and robots or robots and robots for various types of competition and coordination tasks. And finally, the last topic that I just want to briefly mention is something that I'm very excited about, this idea of repeated interactions. I feel like we don't think about it that often. And Andy is thinking about this idea of repeated interactions where we have games where there are elements that are specific to the rule, but there are also elements that are specific to partner, and we are trying to learn what are partner-specific conventions that we can learn. Just like driving on the right side of the road is a convention, what sort of conventions can be learned here? With that, I'd like to thank the group, and I'm going to thank you guys.
Okay, great. So that's just a taste of some of the things happening in the center from my colleagues. And again, I'd like to thank Dorsa for preparing this video. You know, as you can see, there's lots of interesting things going on, lots of things related to, you know, safe interaction and operation of autonomous systems. So with the rest of the time, I'm going to talk about some work that we've been doing in my lab on using formal methods in AI safety. So first of all, just to make sure we're on the same page, let me tell you, what do I mean when I say formal verification? And I think of it as 3 steps. So the first step is to have some kind of mathematical model of the system that you want to verify. And that sounds hard, but actually, if your system is pure hardware or software, or a combination of those two, it's actually very easy because a software artifact or a hardware artifact has a formal semantics. And so you already have a formal mathematical object. Now, if you're dealing with some kind of physical object like a robot or an airplane, this part becomes more difficult. But the good news is that, you know, a neural network is a mathematical object. So this part is easy for that. The next step, step 2, is to specify formally what the properties of the system should be. Now, this may be simple or it may be very difficult, right? And this is one of the challenges I'll come back to. And then finally, step 3 is to prove that the model has the desired property. And this is a mathematical proof. So if you can do it, this is much better than testing because it covers all possible cases. Of course, it's only as good as your properties, right? So if you didn't think of some property and you didn't prove it, there could be some problem. And one piece of good news is that there have been a lot of advances in automated reasoning, which makes this third step much more scalable and tractable than it has been in the past. And now this is, of course, something that I work on, and so it's exciting that there's been progress in that area. All right, so to sort of understand how to put this together in the setting of, say, verifying a neural network, I'm going to look at a simple example. So here's an example of a very simple neural network with 1 input, 1 output, and 1 hidden layer with 2 nodes. So step 1 is we need to, that should say we should create a model of this system, right? So the model is basically going to be representing each node of the network with a variable. For the internal hidden nodes, because they have these activation functions, and here we're going to consider rectified linear unit or ReLU, we have to split those into 2 variables, one for the input to the activation function and one for the output from the activation function. And then we can actually just write a set of equations that describe how these variables are related to each other. So for example, we would say that the x2w, which is the weighted sum for x2, is just equal to the input x1. And we write the equation x2w minus x1 equals 0. Similarly for x3w, and then we write this equation for x4 that just says it's the weighted sum of the 2 outputs. We can also set some bounds. So we know, for example, that the outputs of the rectified linear unit have to be non-negative. So we can set bounds on those variables that they are greater or equal to 0. And then finally, we have some special constraints for the rectified linear units. Essentially, we represent those with this if-then-else construct, saying that the output If the input is greater than 0, the output is equal to the input. If the input is less than or equal to 0, then the output is 0. So this ITE if then else just takes 3 arguments, which are the if part, the then part, and the else part. Okay, so this is now a model of the network that completely captures, everything about that simple network. And you can build models like this even for very large, complicated networks. All right, so step 2 would be then to specify what are the properties that this system should have. Now here I'm just going to assume some simple property, some simple input-output property, like if the input is within the range 0 to 1, then the output should not be within the range from 1/2 to 1. All right, we're going to try to check to see whether that property holds. And the way we do that is we actually negate the property and try to find a counterexample. So what we're going to do is we're going to set the bounds that x1 should be within 0, 1, but then we're going to try to force x4 to be within that forbidden range from 1/2 to 1 and see if that's possible. If it is possible, then the property does not hold. If it's not possible, then the property holds. Okay. Now, this particular example belies a larger challenge with this second step of specification. So in general, it may be very difficult. And why is that? First of all, you may have an easy way to specify something about the system, like the car doesn't crash or hit a pedestrian. But how does that map to a property on a subcomponent of the system, which is this learning component? So that can be quite challenging. The other thing that could be challenging is maybe the property is something that you can't specify formally at all. For example, if you have an object recognition network, how do you prove that it always correctly detects a cat when we don't even know what are the right parameters that would describe a cat versus not a cat? And it may the thing you care about most may not have any formal specification at all. So this is a big challenge for applying formal methods to neural networks, but there is a good place to start. And a good first step is this property of local robustness. So local robustness just means that you have some known data point where you know what the input and output are supposed to be. And what you would like, and this is a property that most networks, we would like to have this property, is that in some small neighborhood of the input point, the network should behave similarly, right? So you don't want to have a bunch of input points that all say it's a cat, and then have some point between those 2 input points that gets mislabeled as something else, right? So what's great about this property is you can specify it formally and you can check it, and you can do this for pretty much any network. So formally what it says is if the difference between a known input x0 and the current input x is less than or equal to some delta, then the output classification should stay the same. Okay, and then step 3 is to prove that the system satisfies the property. Okay, now how do you do this? Well, you need some kind of proof engine. Obviously, you can't do this by hand, right? This is going to be way too complicated. So we need to bring automated reasoning to the rescue here. And we need an automated reasoning tool that can reason about linear arithmetic, because we use linear arithmetic to model the network itself. We need to reason about some limited nonlinearity, like these activation functions, like the rectified linear unit. And so what can do that? Well, off-the-shelf solutions like mixed integer linear programming or SMT solvers can, in principle, reason about these, reason in these two, about these 2 things. But the problem is that they really can't handle it efficiently. So when we first tried to look at this problem, we tried these things and it just didn't scale up at all. So what I'm going to show you is an example of an algorithm that we devised called the ReLUplex algorithm, which takes a known linear programming algorithm simplex, and it modifies it to be smart about these activation functions. And I'll show you how this works. So what we've done here is I've got the equations from this simple example. And then we have this table here that shows a proposed assignment to each variable. And each variable also has some bounds, right? And so we're going to try to find a way to satisfy the equations and satisfy the bounds at the same time. Now, these blue arrows show the two variables that are related to the input and output of the rectified linear unit. And we're going to, in addition, try to keep those in sync. And that's the twist. So I'll show you how this works. So to start with, we find a variable that's out of bounds. Okay. So note that this x4 variable, the current proposed assignment is 0, when it should be between 1/2 and 1. So what we can do is we can just do this update operation to the assignment that changes x4. Now, of course, we have to look at the equations and also update anything that depends on x4. And in this case, that would be x7. So x7 also gets increased by 0.5 because of that equation. Okay, so good so far, except now x7 is out of bounds. So let's see if we can fix that. Now to fix that, because x7 is on the left-hand side of an equation, we first have to pivot it so that it's on the right-hand side. So if we pivot it over here, now we can update it. So we can reduce it down by 0.5, which we do. And that's going to affect this x2a variable. Now, once we change the x2a variable, the ReLU is no longer in sync. So we have to update this partner variable of the x2a. Remember, the x2w is the input, the x2a is the output. So if the output is positive, then the input had also better be positive and equal. Okay, so we update that. But of course, now we have to look to see how does that affect other variables, and it affects x5. So x5 gets incremented to 0.5, and now that's out of bounds. So we're going to pivot and update x5, which we do. That's going to affect both x1 and x6. So we update both of those, x1, x6. x6 is out of bounds. We pivot that with x3w and fix that one. Now notice here that when we change x3w to negative 0.5, the output is 0, and that's okay, because for a rectified linear unit, if the input is negative and the output is 0, that still satisfies the constraint. So in fact, we found a solution, okay? And so there is, it is possible for the input to be within 0, 1, and for the output to be within 1/2 to 1, which means that the property that said that that was not possible does not hold. Okay, so we found a counterexample. All right, so that gives you a little taste of some of the work that we did to come up with an algorithm for verifying networks. And this is actually an exciting new research area. So there's quite a few people working on this. Building specialized solvers or techniques, pre-processing techniques that target backend solvers for somehow being able to verify neural networks, prove things about them, find counterexamples, find adversarial inputs, and so on. And some of the techniques are based on reachability, some are based on search, some on optimization. There's work being done on parallelizing these, and so on. So there's one nice overview at this archive paper that you can take a look at. And I also am happy to talk to people about this later. All right, now I want to tell you one case study of what this is good for, and this is actually the case study that motivated this work in the first place. And this is joint work with Professor Kokendorfer. So basically the idea is he wanted to come up with an airborne collision avoidance system for drones, and working with the FAA on that. And the idea is you have some drone flying in the air. It has some sensor data about potential intruders in the airspace, and you want to give that drone an advisory of what should it do. It could be that there's nothing nearby, so it can just keep flying on its mission. It's the clear of conflict advisory. or maybe it needs to turn, either a strong left, left, or a strong right, or right. Okay, so those are the possible advisories. And for various reasons, Professor Kokendorfer was considering using an implementation with 45 neural networks. They aren't that big. They're about 300 rectified linear units in each network. But the nice thing about the network is it actually had better performance and was much smaller and more compact, so it took up less memory. And both of those were important for this system on drones. Okay, but obviously, you know, it's a little bit scary to the thought of implementing this with a neural network where, again, we don't have this sort of intuition or transparency. So how could we verify them? So the idea was to try to prove that certain properties would hold for all possible inputs. Like if the intruder is distant, then the advisory is always clear of conflict. Or if the intruder is nearby but on the left, the advisory is always strong right. And this kind of proof we considered to be a crucial part of increasing the level of confidence in this implementation. All right, so I'm going to show you an example of what we did with that. But first I want to mention we implemented all of this in an open source research platform called Marabou. And this includes its own custom linear programming engine, support for various piecewise linear functions like ReLU and Max. It accepts input formats from various different tools like TensorFlow. And it has some parallelization and so on. So this is an open source project. You can find it on GitHub. And then let me show you one thing that we did with this. So what we could do is for this collision avoidance system, we did the following experiment. We said, let's start with an intruder who's far away, maybe 90 seconds away from the main drone. And we're basically going to take the entire space of possibilities where that intruder could be and turn it into a grid. Now we're going to assume that that intruder is in one of these grid points far away. Now what we do is we use Marabou for each of the possible boxes that the intruder could be in. We ask what are the possible next boxes it could be in one time step later. And I think the time step here is 1 second. So if our aircraft follows the advisory and the intruder basically stays on its trajectory, then what are the possible next steps that could happen? And then you just keep doing that every second until you get to the point where there could be a collision and try to see what are the possible scenarios, okay? And we visualize this. So the red dot here is the near midair collision dot around the drone, okay? And what we're showing you is basically starting at 90 seconds away, where could the intruder be if I follow the advisory? And yellow means there are lots of ways that the intruder could be in that space. Blue means less ways, and white means there's no possibility that the intruder could be in that space. And what you see is that by the time we get to 0 seconds, there's a nice white area around the red near mid-air collision circle. And so what this actually does is this is actually a proof, a visual proof that there's no way for there to be a collision as long as the intruder stays on their path and the drone follows the advisory. Okay, great. So let's see. I wanted to talk just a little bit about some recent work here where we parallelized this technique and this is a nice technique because it's actually quite general. So the idea is you've got some big question that you want the solver to solve, and it's a hard question. So what we're going to do is we're going to do this divide and conquer algorithm. And the idea is you first use a small timeout and try to solve the entire problem. And that's going to not work. So it's going to fail and say, I couldn't solve the problem. So then what you do is you do some partitioning of the problem. So let's say we partition it into 4 subproblems. Then we increase the timeout a little bit. Okay, so now let's say that 2 of those subproblems we're able to show they're unsatisfiable, they don't have solutions, but the other 2 time out. So for each of those 2, we divide it further, right? So you can keep doing this And basically what this gives you is a way to solve these hard problems by partitioning them into simpler problems. Now, there are several questions about how you would implement this. The first is how you do this partitioning. So one way to do the partitioning is what we call input interval splitting. And what that means is you basically look at the inputs to the network and you divide those inputs into half spaces, right? Now, this actually works pretty well, and we have some good heuristics for how to do it, as long as the dimension of the input space is low. So for these ACAS networks, the dimension is there's about 5 inputs, and this works really well. But for high dimensional inputs, say like a perception network, this doesn't work at all. So we did some new work, and the new idea was, well, rather than partitioning the input, let's actually partition these interior nodes, these rectified linear units, because if we can figure out that one of these is sort of importantly divides the problem into roughly equal parts, then we can just say, well, in one part, let's assume this activation function is active, and in the other, we'll assume that it's inactive, and we solve those 2 subproblems. So one thing we discovered quickly is that it's important to focus on the early layers. And the reason for that is if you fix a ReLU in an early layer of the network, then it has a lot more likelihood of propagating more bounds to later nodes in the network. So you can reduce the size of the problem that way. But how do you choose which network or which ReLUs and which phases? So we came up with this idea of polarity. And basically what polarity does is it's going to look at the current bounds on the variable associated with the activation function. And it's going to see whether the bounds are roughly balanced between the positive and the negative side, or if they're highly imbalanced, right? So if they're balanced, that has a high correlation with giving you a balanced problem if you do a split on this. So we look for polarity close to 0. And we also favor the wider phase because it's more likely to lead to a satisfying assignment. All right, good. Now there's another thing that we can do, which is if we have a bad polarity, then sometimes that indicates a ReLU where one part of the split is trivially unsatisfiable because it has a small range. So we also do this trick where we're going to do a quick check to see if we can solve, assume that one of these ReLUs is either active or inactive with a short timeout, and see if that gives us an unsatisfiable answer. And if it does, then we know that we have to pick the other one. So this is a highly parallelizable pre-processing step that we can do to reduce the overall complexity of the problem. And what this graph shows you is there is a trade-off between how much time you spend doing this pre-processing and how much benefit you get. So, you know, if you do a lot of time doing this pre-processing, the solving time gets short, but the solving time plus pre-processing time might actually be more. So you have to do some trade-off there. Okay, now here's some data showing on a bunch of different networks, including ACAS, some MNIST networks, and some networks that are figuring out how to taxi an airplane down a runway. And what you can see is the ReLU-based splitting is much better than the input splitting on the MNIST and the TaxiNet, which are both perception networks. Now for ACAS, input splitting does okay. Like I said, it works pretty well if the input dimension is low. And then here's showing how well we do with divide and conquer versus just the standard approach. And as you can see, the divide and conquer scales very well. So there is tremendous benefit from using parallelism on these problems. Now we wanted to try something even more ambitious. And so what we did is we deployed parallelization of Marabou in the cloud. And we used a neat platform being developed by some colleagues at Stanford called GG, which basically allows you to describe parallel computation, and then it uses Amazon Lambda to run up to 1,000 short tasks in the cloud. And what we observed is, again, this was just an initial experiment, but for this we observed that up to about 500 workers, we were able to increase the or decrease the wall clock time. So we got more and more benefit, even up to 500 workers. So that, again, we think this is very promising. So one of the biggest challenges to formal verification of networks is scalability, but this shows that parallelism could be a good answer to that challenge. All right, so just to say what's next, so we still are interested in trying to scale up right now. These kinds of formal techniques can handle thousands, maybe tens of thousands of nodes, but still there's a big gap between that and the millions of nodes that are used by many deep neural networks. Like I said before, there's a big challenge in specification. What kinds of specifications can we do? And obviously there are some problems that we won't be able to specify, but we think we can do a lot of things beyond local robustness. So we're looking into that. One really sort of key observation is that even for this local robustness property, most networks don't have that property. And so we really need to look more carefully at how do you even train networks to be robust. And there are some people looking at that problem. And finally, we'd like to look at more applications. Okay, so with that, I'll conclude and I'll be happy to take questions.
Thank you for your talk. And if you have a question or comment, please raise a hand and put your question on the Q&A window. Do anyone have a question?
So while the other people are thinking about the questions, can I ask a question?
Sure.
So I guess the formal verification method applies to trained models. So once you get the trained model, then you can apply your verification method and try to prove the property of the model, right? But of course, some deep learning models are updated very frequently. Like in online training and so on. So
yes.
I wonder if your method can be applied for the models, which also the formal verification, formal properties that falls regardless of the training data set.
Right. It's a good question. So obviously you can take an updated model and redo the verification, but that could be very expensive, right? And so we did have some ideas, again, with Professor Kokendorfer, although I'm not sure how far along we are on this. But one idea would be to include additional inputs to the model that can model sort of the uncertainty. And then what you would do is you would the updates you would do would be to change the configuration of those additional inputs. So rather than changing the model, you change some additional inputs that have the ability to reconfigure parts of the network. Now, if you do it that way, you could still hope to prove something like, no matter how I configure this, however these inputs are, the rest of the network may still have some property. So we thought that would be a promising way to go.
I see. So you have the additional input for training data sets, then you observe the delta of the parameters in the network. I see.
That's right. Yeah.
Okay, thank you.
Thank you. Do anyone have a question or comment? Please raise a hand in Zoom if you have.
maybe I'll go with one.
Oh, yes, please.
Yes. So I have a comment related to the decomposition. Like when you scalability is the key for this to work, right? Yeah. And you seems to have figured a way to do the decomposition, but I was wondering to what extent you find this to be efficient. Like what are the key challenges then? Is it always very likely that you'll be able to find this breaking point where you can actually decompose the problem? Seems to me this would be very problem model architecture dependent. So like maybe comment on the limit on this at this point.
Yeah. So one thing is, one thing I am sort of sweeping under the rug is the complexity is exponential as you grow the number of nodes, and the benefit from parallelism is linear, right? So now you can hope that maybe you get some superlinear, and we have observed some superlinear speed up, but you're still sort of battling, and you need to be smart. Just doing this kind of decomposition and getting linear speed up is not really going to get you to these millions of nodes, right? So we need some additional breakthroughs there to really get there. So like I said, we can scale with this parallelization maybe to thousands, tens of thousands, maybe even hundreds of thousands, but I think we still need some additional algorithmic breakthroughs. Bring in some other ideas from formal methods like abstraction or abstract interpretation, iterative refinement, and people are working on those as well.
Thank you. Any other comment or questions? Oh,
like
okay.
There's something in the Q&A.
Something. Are there plan to be adopted in self-driving cars?
Yeah, good question. So I think, we've been in touch with various companies, and companies like Ford and NVIDIA, we've worked closely with at the safety center, and everybody would love to do some kind of formal methods, right? So the challenge is really scalability and properties. But we do have ongoing collaborations with these companies where we're trying to work out those details. So yeah, we're trying.
Thank you. Any other comments or questions?
Or maybe I have another one.
Oh, yes, please.
Yeah, I can keep going. Very interesting. So the local robustness property that you prove, right? So you observe that in many cases, the models likely fail this. But I wonder how this compared to other approach that are being proposed to look for corner cases using different techniques. To which extent these two could be complementary? Did you look into those other approaches and see what you achieved compared to the others?
Yeah. In fact, we wrote a paper on this that's on arXiv. But basically, to sum up what we found is you can, so the sort of existing techniques that are out there, their big benefit, a lot of them are like gradient based, things like that. And the big benefit is they're very fast, right? So you can run it very quickly and find a counterexample. Now, the disadvantage is that they are incomplete, meaning they're not guaranteed to find an adversarial example if one exists. Whereas our technique is slow, but it is complete. So it can tell you, for example, there are no adversarial examples within some region, which the other techniques cannot. The other thing it's useful for is sort of evaluating these other techniques. So what you can do is you can find what is the minimum distance to an adversarial example, and then run a bunch of other techniques to see which of them get sort of the closest to that minimum. So there are a lot of, I think they are complementary techniques. There are some interesting things you can do with that, yeah.
Okay, thank you. Any other comments or questions? it's almost time, but no questions. Okay.
Yeah, may I ask one more
Yes,
question?
please.
So when you have a specification, okay, and then probably many people are doing is to have the machine learning component, and you have the rule-based component which monitors the input and the output. And if there is a combination of the input output which violates the specification, then raise a flag. What do you think of this kind of hybrid system?
Yeah, I think this is a great idea. If your property is simple enough that it can be handled by a monitor, right, then you should definitely do that. Now, there may be properties that are more complicated that involve some, that a monitor would not be suitable for, and then the formal technique could be used. And you can use them in combination, right? So one idea that we've been looking at is maybe you have a small network that you verify, and you have a larger network that's optimized. And so then you run the larger network, and you have some monitor that tells you whether you're in safe operating parameters. And if you leave the safe operating parameters, then you switch to the verified network, which maybe doesn't perform as well, but it's guaranteed to sort of get you back into some safe operating space. So I think there are a lot of ways to interplay the two ideas. Yeah.
I see. That's very interesting. Thank you.
Yeah.
Thank you. Yeah, thank you for your talk and the interesting discussion. Thank you again. Yes, and shall we have a short break in 5 minutes? And during a short break, panelists can test your mic or webcam.
Liam, can you hear me?
Yeah, can you hear me? Hi.
Okay, cool. Can we see you? I can see your picture.
I can see you. Yeah, I picture you. Nice to meet you.
Mohammed?
Yes, hi.
Yes,
yeah.
Okay, we are good.
Hello.
Okay. I think we already test for the rest.
Okay. In that case, our short break in Okay, shall we start next talk? Our next talk is invited talk by Giacomo Corbo, of co-founder and the chief scientist of Quantum Black. His talk is about ML 2.0, new first cheaper path to build machine learning system. Giacomo, would you like to start your talk?
Yeah, I'll do that. And, maybe, just by way of segue from Clark's talk, I think this follows nicely. As much as we've become exceptionally good at building large, complex software system, and as much as we're seeing the rise of, massive complex systems built around data where the whole value of these systems comes from data, processing that data, ML-enabled services sitting atop that data rather than the software directly. There's an imperative to rethink, how we build these tools, but also how we ensure that these systems, and ML pipelines in particular, ML models, are provably safe and robust. And so that is really what we'll be talking about, how techniques like the ones Clark was speaking to, and frameworks for building ML, for debugging ML, are moving into platform components. So let me share my screen. Okay, so I think everyone can see my screen now. Wonderful. Okay. And I'll just introduce myself very briefly. I think everyone saw the bio and maybe a pre-pandemic picture of me with a little bit less hair and a little bit more weight. But this is, this is, a lot of what we'll be talking about actually is work that I've been doing with a number of different colleagues, and actually with Hiroshi-san, Daisuke-san at Preferred Networks, and a number of others who've been part of this technology council that we've helped convene, that's brought together a number of different people from different academic labs on the one hand, and a number of tech companies, some of them being startups, some of them from some of the largest techs, and to think about some of the ideas that we'll be talking about in the course of this talk, and which is really around how machine learning is changing. A lot of that being tied to machine learning emerging as a software discipline in its own right, with its own patterns and practices of implementation. I'm one of the co-founders of Quantum Black and also the chief scientist. QB is a machine learning engineering services company. Started in 2009 in London. We started in Formula One with 3 F1 teams as anchor clients, started working with a number of different engineering companies. Started working with McKinsey quite a long time ago. So back in 2012, in the first place in the semiconductor manufacturing industry, and then moving into a number of other sectors. And we're 1 week away, as a matter of fact, from the 5-year anniversary of the acquisition of QB. So we became a wholly owned McKinsey company at the very end of 2015, and have been growing and scaling as a McKinsey company since. So we're sort of a center of excellence for a lot of machine learning, and for that matter, a lot of the product engineering that McKinsey does for a lot of the work that we do in this space happens in QB Labs. this is a little bit of a riff on Mark Anderson's point that software is eating the world. And on the one hand, I think a number of you will have heard of the idea of software 2.0. Nice little moniker that was coined by Andrus Karpathy at Tesla, a little bit more than 2 years ago. And what he was describing was really ML eating into software, and what's happening as a lot of complex functionality in complex software systems is migrating into deep learning pipelines, and all of the implications for that. So, some of that being at the level of how the actual programming gets done, and this substitution effect that we're seeing between, what was otherwise, meticulous manual engineering for now what are increasingly compute leveraged activities. So just think of the problem of, hyperparameter tuning as the mechanism that gets us to a final technical implementation of our model pipeline or of our program in a deep learning model versus the ways in which every for loop and if condition in a software 1.0 program is defined. And that has lots of different implications, and that is a little bit less our focus. What we're a little bit more interested in is what happens the other way around. But first on the software 2.0 side, which is something that we've been I think a number of people in the ML community have been very interested in, is that this is one of the general paradigms by which machine learning is increasingly making its way into important software systems. And so there's the very famous example of Tesla and its self-driving systems, but also there was a fascinating paper, a great paper by a number of people at Google that talked about migrating a entity extraction set of components within Gmail into a software 2.0 design. And again, talking about this being one of the important avenues by which they've been able to improve the performance of the system, but also rip out a great deal of technical complexity, just at the level of lines of code, something on the order of about 150,000 lines of code in the process. And for that matter, we also have important parts of, a set of chat services on Facebook that have moved behind API endpoints. Again, the whole idea here being that we've drastically ripped out complexity and also moved much more of the, let's say, the explicit engineering of this and what was otherwise sitting in, a rules-based implementation into deep learning. But we're also seeing the process happen the other way. So we're also seeing, and this is a little bit in line with what Clark was describing, like, software eating into machine learning. And again, this too has, pretty drastic implications for how we think about designing these systems, arriving at final implementations, deploying them, so getting to production deployments and operationalizing these services, and also monitoring them. So it's not just that this is happening at one specific part of the life cycle, this is happening throughout, right? We're seeing this happen in terms of how we collect data on the one hand, in model development and how we think of training data, training models, and then deploying them and maintaining and monitoring them, and for that matter, even a lot of the retraining tasks. Some of you might recall that even where we talk about data collection, this is actually one of the areas where we've got this maybe confound a little bit between software 2.0 on the one hand and what we might otherwise call ML 2.0, which is this software eating into ML. So Chris Ray's lab, Alex Ratner, and a number of others have talked about data programming, and this is really this idea of more programmatic approaches to how we otherwise label data, which is otherwise happening through either very rules-based implementations or mechanical Turk tasks, and trying to get at very flexible but also functional ways and programmatic ways for how we label data, both as a way in which we can automate a lot of those tasks, but also an avenue to improving the fidelity of doing so. And so, but the way in which those techniques are instantiated and made available to model developers is through the kinds of components and tools that we'll talk a little bit more about. And we're putting it firmly in the category of maybe ML 2.0. It's also worth saying that something that is exacerbating this trend, that is accelerating this move to as a service, at least for a certain task, and certainly this is true of many NLP tasks, of certain vision tasks as well. Even time series forecasting, as evinced by the M4 competition, the M5 competition, certainly that just wrapped up in June, and where you've got a number of different, high performing architectures that are extremely compute intensive. And so the idea here is, certainly for NLP, that the performance of these best-in-class models is moving us into a place in which you don't want to take on, nor should you have to, the training requirements, the training requirements from scratch on any given data set. What you want to be able to do is either do incremental training or perhaps in many cases little to no training at all. So, and that's as very specific examples just around model endpoints. But as I mentioned before, like we're seeing this across the model development lifecycle, and in fact, at several layers of the stack. And so, we're seeing the emergence of a much better defined tech stack where we have different components, and that a lot of these pipelines are ultimately deployed into the cloud, that we have now, microservices architectures that are well adopted. Kubernetes makes it easier to have a lot of these components be interoperable in a way that interoperability is maybe one of the things that made it difficult to do anything but deploy, a single monolithic platform, and whatever functionality you had within that was what you developed and what you and even maybe was strongly tied to the runtime engine via which you productionize something. And so we're seeing that there's an opportunity to compose model platforms and to have specific components, whether these components are around how I label data on the one hand, but also in support of specific models And it could be certain model activities like trying to help automate hyperparameter tuning, but even having something like a specific model framework with a specific embedding. So think of TabNet available as a native service in the cloud, which it is on GCP. Altogether we're in a place where you can, organizations that are looking to deploy models are having to do less and less implementation for a specific model, for a specific data pipeline, and that a lot of the important, a lot of how that pipeline is composed, both at the level of model itself, but also a lot of the supporting infrastructure in order to be able to productionize that, whether it's around providing explainability, or satisfying an explainability bar on the one hand, whether it's around productionizing that model and integrating it with some other downstream integration endpoint, whether it's just at the level of monitoring that pipeline for any number of things that could go wrong, whether it's around data drift or looking for other issues that might happen to your input data. Increasingly, we have platform components that are solving those very specific challenges and that obviate the need to solve those problematics from writing bespoke code that is strongly tied to that data pipeline, that model pipeline that a dev team is working on. But the fact that we have an increasingly interoperable environment and mechanisms by which we can stitch together these components means that we've got a vibrant and increasingly complex ecosystem. And so a lot of this, a lot of the kinds of platform components I'm talking about are increasingly being provided as supporting platform tooling in the cloud. But it's also the case that you have a number of different horizontal startups. I would call out, for example, Determined AI on the one hand, for deep learning training workflows, or Selden, for example, for let's say Selden Core for deployment and productionization of ML. You have higher level, you have specific components, whether it's things like Optuna on the one hand, or Raytune, or HyperOpt, that are tackling a specific activity. So hyperparameter tuning. And then you also have specific model frameworks, and I would call out, let's say, NVIDIA's Merlin as a model framework built on, that's tailor-made to build a certain category of recommender systems and highly scalable recommender systems. But that puts us in a place where leveraging that framework means that an implementation team looking to build that category of model is ultimately putting down much less code. In fact, you've gone from what would otherwise have been a pretty complex implementation to putting down 100 or so lines of high-level API code, at least for the data transformation part, exploiting NV-tabular, which is part of Merlin. But the point is that a lot of that tooling is exactly the kind of tooling that a lot of tech companies have had to build themselves. And those tech companies, if you think about Uber's building Michelangelo, if you think of Netflix building Metaflow, if you think about how Apple describes the leverage that it's gotten from Overton, a lot of this is around solving specific specific challenges in the model development life cycles and trying to find ways in which to build supporting infrastructure and platform components to be able to either change the profile of developer, disaggregate teams, make people a little bit more autonomous end to end, and decouple some of the dependencies across very different technical profiles to unlock scale within those organizations. The point is that a lot of these specific platforms or these organization-specific platforms have, a lot of them have moved into open source software. Metaflow is a very good example. Michelangelo, in fact, Michelangelo has spawned, Tecton, and so you have a lot of this is part of the very vibrant ecosystem that I was talking about, again, which puts us in a frame where a lot of organizations that are looking to tackle ML and not to do it in the context of a few different models, but are really trying to address the challenges of doing this at scale to support, data science applications and the development thereof across a very large organization, trying to, enable maybe a relatively small engineering team, but to move at velocity throughout an organization and be able to productionize things pretty, quickly and to keep moving. The idea of being able to move a lot of the technical implementation complexity to higher levels of abstraction, so that a lot of the data science work is now within, and the techniques that need to be navigated in order to be able to solve those problems are now within the reach of maybe data scientists and developers who are not deep practitioners in any of those specific techniques. And so, think of the higher level abstraction frameworks enabling or the move to models as a service, as enabling developers who might be relative neophytes in any, in an LP, for example, or in vision, to be able to now solve hard vision and NLP tasks. And so, all that I'm referring to here are, there are a growing set of options for many different varieties of organization to be able to implement ML at some scale by building, fit for purpose platforms that are matched to the talent that they have, the talent that they want to be able to bring in, and the kind of data science applications that they're looking to implement. So this is really what we're talking about. And I'll speak to a few different examples. I mentioned data programming before, and this is Snorkel, which I think some of you will be familiar. An open source framework, and now a commercial platform that helps to automate a lot of data labeling tasks. A lot of it enabled by weak supervision. And so, this is a specific application where you would otherwise have a much more costly, but also maybe much more more brittle and manual effort for solving this task. And there's the citation is at the bottom here. It's a fantastic paper, but it's just as an example for we can now get into a frame where we are much more deliberate about the data that we collect for the specific purposes of building models on top of that data. There's another, within data programming, we also have, the idea of moving a lot of the data collection into, exploiting active learning for that. And the idea being to hone in and be much more targeted on the most informative samples. And so not to, collect data indiscriminately, but to be much more focused about what data we're ultimately after. Elsewhere in the development lifecycle, so much more about productionization. So I mentioned Selden before, and this, is a public case study of Capital One using the platform in order to be able to, deploy models effectively. You've got, I mentioned Michelangelo before, and that's the, this is the reason for which, Uber created this as well. Again, having created at a point in time where a number of outside options just didn't exist. And maybe, going back to NLP, you've got a pattern like this one where it is possible to, to get to a very specific workflow. This is highly tailored to UK visa and immigration, but involves stitching together a number of different components, again, with a view to minimizing the amount of implementation complexity that UKVI has to specifically navigate in implementing this workflow. And maybe as a final example, this is just to say that we're also seeing ML services, increasingly being part of, what we wouldn't recognize as machine learning platforms. And so I think Einstein, as part of Salesforce is a pretty good example where, for a number of different categories of model, including things like a churn model, but also to, a sales pipeline and trying to validate the the integrity of that pipeline, the likelihood with which any specific opportunity is going to convert within an amount of time, that you don't, instead of every single organization having to solve facets of, the same problem on its own data set, that you're moving into a place where a lot of this is basically, GUI, building in a GUI, where analysts, for that matter, are moving with specific components, where there's very little programming. So this is almost like a no-ops view of where some data science and some ML development is going. And all of this isn't just about the compounding effects of marginal productivity. It's also about the ways in which, and the pace at which a lot of the technical the ways in which technical challenges are being addressed, like the fact that we're seeing a lot of the most complex ML being democratized in the way that they are, also means that there were previously unattainable capabilities, unattainable because of their sheer implementation complexity, that are now increasingly possible. And I'll just mention two very quickly. The one on the right-hand side is, work that NVIDIA's talk about, but specifically Anima Anand Kumar's lab at Caltech, and she's also affiliated with, I think, being the chief scientist of intelligent systems at NVIDIA. She and her collaborators have worked on low-dimensional tensor decompositions for for RL in ways that allow the combination of optimal control strategies and reinforcement learning, there's nice results around the task-specific problems that that allows you to solve. On the left-hand side, we have work that we've been doing since May of last year, and this is work that we've been doing with an America's Cup team, so Emirates Team New Zealand, the current defender of the America's Cup, and they'll be sailing very soon in March of next year. But the work that we've been doing is centered on building a digital twin using reinforcement learning, effectively teaching a bot to sail the boat in a high fidelity physics engine. And it's it is a hard control problem, and one that was solved via an SAC framework implementation. And all that I would point out is that it's very compute intensive, and the way in which we were able to solve that problem and the specific composition of the pipeline and the underpinning stack is what I would describe as ML 2.0. And so where a lot of the both at the level of how the infrastructure was managed, how the jobs were parallelized, activities like hyperparameter tuning itself, a lot of that was leveraging best-in-class components and services in ways that still meant that this was a relatively complex application for us to develop, but also brought it within the reach of feasibility and implementability in ways that would have been difficult otherwise. So I think I've tried to describe that the implications here are pretty far-reaching, and fundamentally there's a lot of organizations have to think in the first place as a function of what they want to build, of building a highly optimized ML tech stack, which is also a reflection of the developer capabilities that they'll need and the specific workflows within which that talent, that human capital will operate. And when we talk about the delivery protocol or implementation workflows, development workflows, a lot of how to operate on top of that tech stack is what otherwise would what I would describe as or what is often described as ML ops. And this is still an emergent field. Like a lot of the DevOps is much more mature. We have a much better understanding of how to build software generally. And as Clark described earlier, there's AI systems or ML pipelines are different, right? And to the extent that they're different at the level of code, but also how they're implemented, it has pretty far-reaching implications for what are the optimal ways by which developers should be navigating different parts of the model development and deployment lifecycle. So you know, we're going to have I think a panel discussion in just a little bit, and maybe we'll touch on this a little bit later on. But you know, a little bit, just maybe 3 questions on where I think this is going. So, you know, for a lot of different organizations, where is the competitive differentiation here? Like, if it's not at the level of you know, specific models, as many organizations might have thought, you know, what is it that they should be looking to stake a competitive advantage? And I think, you know, for many organizations, it's at the level of, you know, having the appropriate infrastructure and the right team of developers to be able to move at speed, to be able to experiment more quickly, and for that matter, this places, I think, that much more of a premium around data, and data in support of those experiments. At the level of the implications for domain-specific applications, I mean, I think that a lot of the horizontal tooling and a lot of what I've described is horizontal tooling, isn't use case or domain application specific. Then I think what we're going to see is you know, the verticalization of a lot of this tech. I think we're going to see you know, much more productization and very domain specific productization, and you know, just because it's possible, just because the code footprint for a productized version of a model, you know, that is within reach of a lot of different organizations and relatively small outfits. And what you may end up getting to is an opportunity for much more vertical integration. In fact, you may see much more vertical integration end-to-end, precisely because you know, of the premium or the growing premium that you know, that for data and for how data is collected. And maybe finally, you know, where is all of this going? Like, what is the target state or the target operating model for a lot of development? I mean, I think it will look different in a lot of different organizations, but I think we are generally seeing to a lot of these platforms are, and as much as we talk about MLOps now, I think the requirement for engineering resources in the loop for a lot of different organizations is going down. Like, we're going to, you know, what is otherwise, you know, called no-ops data science, at least for many different applications, not as it applies to maybe things like, you know, building autopilot systems or anything of that complexity, and where you have that kind of, you know, highly bespoke infrastructure. I mean, that's not really what we're talking about here. What we're talking about is most of ML, most data science as it is practiced by most organizations, where we're talking about, you know, relatively more parsimonious data pipelines. But, you know, within, you know, with that caveat, we are seeing a lot of that platform enablement is moving to much more disaggregated and atomized teams. We're going to move away from a world in which we think about standing up relatively large cross-functional teams that bring a lot of different technical profiles together, data engineers and data scientists. You know, even within QB, we make the distinction between data scientists who are, you know, first and foremost quants and very good modelers. And we make the distinction between those and machine learning engineers who are, you know, first and foremost software engineers. Very good quants, but where the accent is placed much more on software engineering and being able to write production quality code. And in order to be able to move out of a world where, you know, models have to be refactored and defactored before they're moved into production, we have those resources brought together into a, you know, single fighting unit to develop these models and quickly being able to operationalize them. But you know, these MLEs are, you know, what is otherwise, you know, often called type B data scientists. Well, I think by and large we'll see a lot of data science being, being within the reach of type B data scientists. In fact, type A data scientists get to a place where they're the ones who very often have specific training within within ML, who will have a PhD. And I think there's plenty of organizations that are going to continue to do a great deal of very complex stuff. But by and large, I think the trend is towards democratization and towards the software engineer being able to do a great deal of data science. And again, we've disaggregated, the platforms have disaggregated the teams. And so instead of having to have these relatively large teams and lots of dependencies across, in the workflow between these technical profiles, I'm getting to much smaller teams and people who have end-to-end responsibility. An individual or two data scientists working in tandem, being able to get at the data they need, being able to develop a model, being able to test it, being able to operationalize it, perhaps even themselves, with no liability or dependency on anyone else. So I realize that we might be a little bit behind for time, but I will pause there for questions.
Thank you for your good introduction to ML 2.0. Although anyone can ask a question during the panel discussion, do you have any quick question on the talk?
Maybe one.
Yeah, please.
Just a quick start. Very nice overview, Giacomo. I really enjoy, especially the 2.0 ML 2.0 part on the rest by the end. So it seems that we are observing an explosion of component and framework that are specific for different aspects of the ML workflow that people can use. But I wonder, what will you say to people who get worried by the fact that we are pushing a complex, maybe we are oversimplifying a complex technology for the mainstream? Let me rephrase. So a recent study shows that many people are actually using ML as data scientists, different companies, were not, and in general, are not aware of all the uncertainties that are in the model or the variability that they have to deal with. And another issue is most of ML models fail silently. So there are many ways of doing things wrong. That doesn't necessarily crash, right? So the system, you still end up with something, right? Which sometimes works, right? Maybe depending on what your validation set will be, you have the impression that it works, but actually it's totally off. So by doing this oversimplification, do you think that there is a higher risk that we end up with a lot of misuse of this powerful technology, which down the road end up hurting us? What will you say?
Absolutely. Like, there's a huge risk that we're oversimplifying things. I think, as you were saying that, I think you might be thinking about, the same paper that I think a lot of other people maybe were also thinking about, which is the paper released 2 weeks ago by about 40 researchers at Google that talked about the prevalence of underspecified ML models. I think that's pretty amazing to me. Like, if an organization like Google can get it so wrong in so many different circumstances, then what hope is there for so many other organizations, right, to get it right? And if it's often talked about that recommender systems, for a variety of different reasons, in many different contexts, recommender systems have a very steep performance degradation after retraining, which is one of the reasons why you want to very often move a lot of recommender system pipelines to to continually train pipelines, or as close to continual training as possible. But in light of the paper a couple of weeks ago, some people have posited that, well, actually what we, this general phenomenon that we might be seeing is not tied to anything around, let's say, the non-stationarities in, let's say, preferences, right? Or in the underlying dynamic, that a lot of this actually might be tied to, intrinsic instabilities in the model. The fact that the models themselves might be underspecified, like severely underspecified. And so we're fooling ourselves, I think, in many contexts with how well our models are performing on deployment and the reasons for which we see degradations in performance post deployment. So, I mean, Futse, I absolutely take your point, and I think it means that if anything, it speaks to some important shifts that have to happen in terms of how we develop these models, that we are moving into a place where we are maybe some of what I'm talking about, even at the level of more targeted data collection, it is precisely because a lot of statisticians are uncomfortable with data science and how it's often practiced, in that you're collecting, you're maybe training on data that was collected for very different purposes, right? So much of data science is exploiting natural experiments. And I think, a lot of statisticians would point out, so many different reasons why natural experiment data has its limitations. And I think all of those statistical, those problematics that econometricians and statisticians know very well, I think aren't as well understood within the data science community. And I think the ways in which we get better, though, will also involve the kinds of platform enablement that I was talking about. Like, for example, even if I think about explainability, yes, there are, right now there are a lot of different implementation teams that are doing, have a lot of good enough ways, but pretty bespoke and ad hoc ways for answering the, questions around explainability and being able to show bias. And the ways in which we introduce rigor into the system, I think in some way, is by having a lot of that technical complexity abstracted from people and moving into platform components. But all of that, still needs knowledgeable operators at the wheel, right? We still, in a lot of different, and it's one thing if I have important biases and skews in my model when it comes to a recommender system, telling me, the things that I might like to purchase along with a certain item. But when we're talking about a lot of mission critical systems, including, mortgage affordability tests and credit risk tests and any number of other important implications with possibly adverse effects on people, and I think these remain open challenges where a lot of the technology remains incredibly immature.
Definitely, I think that's also a very nice transition to our panel.
Yeah.
Right?
Let's get started. Panel discussion.
Okay.
And, it's on our software 2.0. Could you be a chair of this discussion?
Yes, please. My pleasure. So welcome back, everyone, if anyone left. So we'll have an interesting panel. We have 4 exciting, I hope it will be controversial, panelists. And we'll be discussing about software 2.0. We just started talking about it. So we'll try to push maybe the envelope a bit further to see how far we think this paradigm will lead us. Right? What should we be envisioning? I would say maybe what are the pitfalls along the way that we have to to overcome to make this a reality. So our panelists will be, we already had our invited speaker, Jacobo, and we have Mario Masensei, who is in the panel. From Prefer Networks, we have Mohammed El Gaish, who is Director of AI at Cisco. So we have the Cisco view on the problem. And we have an academic, my dear colleague Liam, who is a Canadian chair on AI in University of Montreal. He has done a lot of work on automated driving systems, so he knows his share of issue around software 2.0. So before the open discussion, we have 5 minutes live talk from different panelists for statements to kickstart maybe the discussion. I hope some of them will be controversial. And so let's start. So Kaz, are you broadcasting? Who is going first? Maybe Jacobo, I think you already had your last slide.
You've already got my position statement.
Maybe Mariam-san can be first.
All right, so let me give my 5 minutes talk. Let me see if I can share my screen. Here we go. And okay, so I am Hiroshi Maruyama, working for Preferred Networks. Let me give a little bit discussion about the terminology. There are sometimes these words, AI, ML, software 2.0 used interchangeably, but I think it is important for us to make a clear distinction between them. So for me, AI is a research field, and it's not a system that uses AI technology. Of course, we have the technologies coming up from the AI research, but I think we should better to use a different word for the technology rather than the research field. Machine learning is, of course, one of the technologies for inductive programming, and it is based on statistical modeling. Software 2.0 is a new paradigm in automated programming, and I am going to a little bit go further in this view. So software 2.0 is, I think, the attempts to automate the programming, and by searching the programming space. So traditionally we did a programming by manually coding the program. On the other hand, in software 2.0, programming space is over here, and you search this space, the solution which satisfies the given specification. And of course, we have to have a lot of computation behind that. So speaking about, so that it's very important to be able to give the specification, okay? Then let me briefly review what we have done in specifying what the program is. And one, very, very basic way of specifying a program is just coding, writing the code, or by specifying the execution steps. Or in a traditional software engineering, we have the model-based software development, which means you give the mathematical model, and that is semi-automatically transferred into the execution code. But assumption behind this method is that we have the complete specifications, or we can write the complete specifications. But then, the world is much more complex, and sometimes we have to give the specification by input-output examples, and we have a test-driven development, and also we have a statistical machine learning, and this is part of software 2.0. Sometimes we give a specification by, giving an external oracle. So reinforcement learning using the external simulator is one example. Or agile programming is a kind of external oracle. Our customer says this is no, I don't like this, and you got that feedback and do the programming again. This is a manual, but reinforcement learning and other optimization techniques are more automated. But important point is that we handle the situation where we have the incomplete specifications or conflicted specifications, and that's the a very difficult point in software 2.0. So that's why I believe we have to have a new engineering discipline. Let me give an example of another engineering discipline called civil engineering. When you cross a bridge, you don't much worry about the bridge is falling down, because there is a big body of knowledge called the civil engineering behind it. And these are the volumes of the civil engineering handbooks. And most of the pages are spent on the theories, like structural theory or material theory and so on. But there is a very small table called safety factor. And this is a safety factor table. And I think the point here is that the civil engineers know a lot about civil engineering, but they also are aware that their knowledge is not complete. That's why they have this safety factor table. And if you apply this safety factor like 3 times more strength than the theory says, once you get that point, then you can convince the society that the technology is mature to be adopted by the society. So I think the same thing should be done here for machine learning. And of course, we don't know much about the we have the incomplete knowledge why this machine learning system works. But by demonstrating the usefulness of the machine learning systems and the safety and so on, by doing that, I think we can convince the society. And that's why we are here. We are discussing about machine learning engineering. That's my position. Thank you.
Thank you very much. Thank you very much. Interesting. We will touch on that in the discussion. So second, Liam Mohammed.
All right, let me share my screen. Okay, so for my talk, I actually thought during this workshop that most of the previous talks covered the superset, and I'm gonna try to get something new. And I've been thinking about this for the last 5 minutes, like what are the new things I can provide in my very first talk. So first, let me just quickly introduce computing with data. So besides my work at Cisco as director of AI, I also I'm teaching assistant part-time at Stanford University, and I like writing a lot. So this book is co-authored with Guy Lebanon, and basically we try to maximize the overlap between 2 disciplines, data science and software engineering, not just data engineering, but software engineering. And I really liked from Giacomo's talk, the point about like bringing these like 2 disciplines together. There's going to be a very interesting intersection between them. And if it's not necessarily for creating a new discipline altogether, at least overlapping of knowledge and overlapping of understanding of what it takes to build an entire pipeline that solves an AI-based or big data-based problem. So for my talk, I wanted to focus more on the dev ecosystem 2.0. I think the idea of having, by the way, great survey of like what startups and horizontal platforms are there. And I think it's a great starting point to have this progression, an increase in the ecosystem, flourishing ecosystem for helping AI solutions. But I also couldn't help but like feel that the fact that we can actually summarize it or put it all in one slide is sad, because we need the explosion that has happened for traditional software, rule-based software. It's going to be much, much harder for you to go and figure out that map for all the systems that we have today that allow us through the life cycle of software 1.0 to produce something and make sure it's like verified, and you get through the entire like speccing, development, deployment, monitoring, debugging. The ecosystem is, of course, huge for the 1.0 ecosystem for development of the rule-based systems. If you think about how we can like look at the stack or the ecosystem, if you think of hardware challenges, we have had a lot of AI accelerators, right? So the TPUs, GPUs, what have you, have been built specifically, including like your phone now and the new MacBook. They have neural engines and so on. These accelerators are great for the ecosystem. They allow us to do way more in much less time, but they also bring about a new set of challenges. Like back in the day when you have, let's say like, a basic bug, that you file a bug and you say like, here's how to reproduce that bug for a rule-based system. A lot of the times you include in the bug details the hardware and the software version and the SKU and certain ways or certain conditions under which if you repeat the same reproduction steps or reproduce the steps exactly the same way, you will find the bug again. So with AI and specifically with these like highly parallel systems, like think of a GPU when you're doing a simple thing like floating point sum, right? It's non-deterministic. You can run it multiple times and you get multiple results because of the precision and the parallelism constraints we have, or because of the way we actually represent the floating point. It can change based on the order of which you aggregated them and yield a different result. So there is a lot of like interesting challenges that have been kind of abstracted away in traditional software, but now we have to be very careful about. Speaking of which, thinking in probabilities. So as you mentioned in the workshop description and previous talks, rule-based systems are deductive. You can have like TLAs or other like systems for verification, and you can show even for a distributed system that it works correctly, and you can prove that. We're thinking of inductive systems. We're thinking of like how to reason about the world via a sample, and you get some probable output, and you're basically trying to verify that this is more or less within the boundaries of what you expected that system to produce. So we have to design for safety, and I really liked the previous talk talking about the safety factors, and we learned a lot, like resonance frequencies, and we had disasters and bridges, and that's how like these things became an acknowledgement of like, we don't know what we don't know, and we have to like provide some safety net or some guardrails for the future, just in case we miss something. It's an incomplete knowledge, so you cannot make complete deductions or complete conclusions. And for that, we think of like applications of, let's say, generative models. If you have a generative model that produces text or even a speech model, like a speech recognition system producing text, and there's a probability that it might erroneously produce profanity. Imagine if you're just speaking like I am speaking right now, and there's closed captioning and it starts writing or displaying profanity because it made a mistake. Well, your safety net should avoid that embarrassment by masking out these kind of embarrassing errors and making sure that you do not go into that territory. So you need some sort of guardrails, and I would say these are going to be rule-based, of course, and super important for controlling the output of what these non-deterministic systems can produce. I also think of GitHub and just all of these systems that we had popularizing open source and collaboration of software. Specifically, like if you think of of course we had SourceForge and other things before, but the role they play in the ecosystem is extremely important because they show you like a rating and collaboration environments where multiple developers can come in and collaborate on forks of the same project and so on and so forth. We need something very similar for data. We need a kind of data hub where you can imagine like in GitHub when you have like the lineage of the code, right? And the change sets and how like each change affected the rule-based system, you need some sort of data lineage as well for data systems, understanding like how to reproduce your DAG, your kind of workflow or pipeline, and the ability to fork the data and verify that it works for your own fork and so on, but also ability to trace back, just like you have Blame in GitHub, the ability to trace back data lineages. Like we mentioned that multiple times during the talks, that your code is basically writing itself using the data, right? So how can you go back and pinpoint exactly which change in the data set or the other code artifacts caused your system behavior to change over time? And the other dimension of the GitHub-like systems is they made integration with the rest of the ecosystem much, much easier via webhooks and CI/CD integrations and so on. So the development cycle became much easier for the ease of integration that it provided. And we need something as easy for data science and AI projects where you can actually integrate CI/CD kind of pipelines, but instead of thinking of how you can test like a unit test and integration test, how to do a probabilistic, maybe statistical test, right? Like thinking of the, maybe a t-test for your data that you captured in test eval and subsampling from production data and thinking of like, okay, do I have concept drift when I'm releasing this? Is it going to cause any issues for the new deployment and so on? So if you think of the other ways of testing, you can think of simulation testing. We talked a little bit about self-driving cars, and you might have a new modification in the system. So instead of waiting on going outside the real world, you can build a city and simulate like within bounds, did the system operate as expected or not? These are all interesting, modifications to existing ideas. I don't think there's anything that's extremely novel. The challenge is the ecosystem is not there yet. We need to build these systems and make them as easy to integrate with. And maybe there's a little bit of a mindset shift or a paradigm shift in the way we think about these artifacts as well. So there's tracing and logging, observability is extremely important, profiling. These apply to traditional systems as well, but they became more important now when you do not have a full understanding of coverage. Like when you're designing the system for a traditional system, you can think of corner cases, combinatorial testing, and you can figure out here's my domain and range. And you can easily assert that these things map to your expectations. But with the ever-changing behavior and the very long tail for all of these problems that AI provides solutions for, it's going to be much, much harder to test for everything ahead of time. So even though you walk into the design room with specs and thinking about the tail and how can we provide safety, you cannot assure, without certain observability that you have been able to see all of the possible outputs, and you need to understand that sometimes in real time with monitoring and profiling. Instead of just looking at memory print and kind of CPU use and exceptions count for traditional software. In addition to all of this, you also have to look at the input distributions and output distributions, understand emerging trends, unique values, why did they produce such things, and maybe if the classes that you have shifted. The concept drift is extremely important, and not just in data, but also in the labels that are in the real world, and how can you make sense of these. I think observability overall is the line of defense that you have to have. If you have weaknesses in the rest of the system, they will, at least by the mere act of observing what's happening, will push you to think more and more about where else do I need to fix things. So in conclusion, I think I did not coordinate this with Giacomo, but I think we have the same sentiment. We have somewhat mastered software 1.0, and we're still clueless about AI and data sets. It's just gonna take time.
Thank you. Interesting stuff in there. The need for a lot of engineering to actually try to compensate the limitation of the current ML models that we're having. Lyle, do you want to pitch?
Hi there. So my name is Liam. I'm a professor at the University of Montreal. I don't do screen sharing, so you can just maximize me. So I'm going to talk about something a little bit different. I think there's a lot of interesting connections. I've really enjoyed a lot of the talks we've had so far from all of the panelists. So let's go. So I do robotics and deep learning, and I put software 2.0 in the title because I felt like I had to, but I don't really know that much about that. So, but I've learned today, you know. But thank you, Futsi, for inviting me. So the objective, you know, in robotics is to take, you know, robots from environments that look like this and put them in environments that look like this, right? And to date, the number of actually successful consumer robots that actually have deep learning systems on them is extremely small, very, very limited. So a traditional robot system has a certain set of abstractions. So the normal way that we do it is we separate the like world from the plant, and the robot is the world and has actuators, and it exists in an external environment, and it has sensors. And then it perceives the environment through the sensors. So we need a perception system. This is actually the area where deep learning has made the most inroads so far. Then we have to take all these measurements that we're getting from this perception system and assimilate them together into a coherent estimate of the world. And we have to use that estimate to make a plan about what we're going to do. And then we send that plan to some kind of controller, and we actually execute control commands. And the nice thing about these traditional paradigms is that we could make, like, a very common theme that's been repeated in this workshop so far is that we could have guarantees about a lot of the things that came about the contracts between these abstractions in this like typical approach. So what are the desiderata then for a data-driven robot? Well, the first and foremost thing is that we have to guarantee that it's safe, particularly if it's a safety critical system like a self-driving car. And this guaranteed word is like a very hard word, right? Like, what does that actually mean? In practice, it means probabilistically guaranteed. We want robustness to real world nuisances. So when we take it outside, it doesn't matter if it's raining, it doesn't matter if it's sunny, if the sun's right in the camera, whatever, if there's like a giant lightning storm, or if you're at the top of Mount Washington, it's supposed to work in all of these situations. We want both the environment to be able to scale in complexity and also the tasks that a robot can perform to be able to scale in complexity. This whole thing has to run in real time. So this has to be like on embedded GPUs and stuff. And then like last and maybe most important in some scenarios is that we have to have some realistic way of getting a data set. And for physically embodied systems like robots, this can actually be really challenging because getting the scale of data that we need to train these systems can be laborious and dangerous and stuff. So I'll give you just a quick overview of what we do in my lab. So the research themes are trying to address some of these challenges. We try to build and learn efficient representations for robots. We try to think about and quantify and reason about uncertainty, and I'm going to talk about that in a little bit. We try to build efficient pipelines for learning and simulation and transferring that knowledge to the real world. And we also think really hard about evaluating robotics benchmarks along the same line that like reinforcement learning has been held to this standard now that it needs to be reproducible. We need the same standard with like embodied physical systems, but it's extremely challenging. In applications, I've worked on autonomous driving. In particular, I work on this problem, simultaneous localization and mapping, a lot in my career. I won't get into the details. And now I'm just starting to think about manipulation in more complex, higher fidelity tasks. Okay, so let's talk about safety, right? Like this is the thing that's supposed to be the reason that we're making this autonomous car, even though it's like a quick sidebar, it's really not. So everyone wants to like talk about this trolley problem, and we can think about like really connecting it with the first keynote. Like there's been decades of work of formal verification of how we can guarantee safety, and everybody wants to talk about how the safety, like the self-driving car is going to have to make a decision about whether it kills a grandma or a baby in a stroller or whatever. This is like largely unproductive, I would argue, but there is a version of this problem that is productive. So I'll put it to you as the probabilistic trolley problem. So let's say you're in a situation where you have option A, where you kill a pedestrian that's on the road but shouldn't be, so it's not your fault. And you have option B, where you swerve and you kill somebody who's on the side of the road and you kill them and it is your fault. And there's some probability P that you'll kill this person B. You're going to kill the pedestrian with probability 1, but it's not your fault. So this value P really matters. If you're guaranteed to kill somebody if you swerve, you're definitely not going to swerve because the person in the road, it's their fault. They like should admit more blame. But if there's zero chance of you killing anybody if you swerve, then you're definitely going to swerve, because then even though it's this guy's fault, guy A, poor guy A, you know, you can still save his life. And so, you know, there's some like continuous, there's a decision value here for this value of P, which is why I find this problem really interesting. But the underlying thing here is that we actually, a prerequisite for even thinking about this problem is that we have calibrated estimates of uncertainty. And this is really hard to get from deep neural networks. So we've been thinking about this a lot in the projects that I have with Futse. We've been talking about the different types of uncertainty that you can think about in deep neural networks. And they're very different than traditional systems, because now not only do we have the uncertainty associated with the underlying process, we also have a certain uncertainty associated with the model, whether your model is trained enough, whether you're in distribution or out of distribution, and how much you can trust the output that you're getting in a specific scenario. And these things are very hard to predict, and especially hard to calibrate, which is like a different issue. Okay, so point two, the role of simulation in robotics. I think, you know, roboticists always viewed simulation through an ambivalent lens. Like in one sense, it was just a plaything that unless you did it on the real robot, you weren't a real roboticist. That's the way it used to be. But now we have these robots, these simulators, sorry, that we can actually use to teach robots things. And then we can transfer that knowledge onto the real robots. So we can really save time. But how to teach them is actually pretty tricky. So we might show them how to do something. We might use reinforcement learning. On a real robot, this gets really expensive and slow. So this is an amazing project that was built by Google, where they had like, I don't know, I forget the number, like 20 of these arms sitting in a room for like 3 months, just picking and placing objects, you know, all day long. But the ideal would be if we could actually train this thing in simulation. So I don't know if any of you have seen this amazing video of this robot doing the Rubik's Cube, but this was trained about like 98% in simulation and then 2% on the real robot. And so this overcomes a lot of the problems associated with working with real hardware. Unfortunately, the value of data that you get out of a simulator is significantly like less than the value of data that you get of actually doing an on-policy rollout of a robot. And then somewhere in between those two is what I would call like off-policy rollouts, which is actually what we get, say, if Tesla collects all the data of people driving, like it's not the actual learning agent that's in control of the system. So it's like another agent, an expert that's giving them data, which is very useful for sure, but also imposes some distributional shift problems. So there's sort of two main approaches that we're investigating in my lab for crossing the reality gap. And these are like, I don't think that there's like this is a more general problem than just transferring agents from simulation to real. Really, the two approaches are, you can somehow learn the mapping from one modality to the other. You actually explicitly learn it. You know that there's a data distribution shift and you learn what it is. Or you learn to generalize across. And so in the first case, like a lot of people use kind of these GAN type models to actually make the two data regimes, either simulator or real, be indistinguishable. And in the second case, maybe you use something like domain randomization that makes your system robust. Okay, last point. I know Futse, I'm over. I knew I would. So just thinking about actually, evaluating and benchmarking a robot, a physically embodied system. So you like a lot of the problems that you guys are talking about, they're already really hard, but now like adding that element of evaluation and benchmarking onto a real physical system is even like another degree even harder, because you can't standardize the environment. It's very hard, like when you're outside of lab settings and things like that. So in this frame, we've actually made a sort of an effort to build benchmarks and start a conversation, particularly around autonomous driving, and to get people from a wide variety of different backgrounds to think about and talk about how we can actually evaluate progress, short of just looking at the latest YouTube video that Elon Musk has published and trusting that that's how well the system works or whatever. So this is a AI driving Olympics competition that we have run now at NeurIPS, which is a machine learning conference, and ICRA, which is a robotics conference, for the last 3 years or so. And so in this setup, we have a simulator, we have this toy little robot, we can evaluate your agent in the cloud, We can evaluate your agent in a remote lab that's standardized. You can just like remotely submit your agent and it'll get evaluated. We have a simulator, we have logs. You can do whatever kind of machine learning pipeline you want. We provide baselines and everything like that. And to somebody else's point, I forget who, but like somehow like standardizing things, I think it was Mohammed, the making this barrier of entry for getting some kind of standard reproducible machine learning pipeline in place and actually evaluating it in a standardized environment, I think is like very hard, but I think we're on the road to doing that. So this is like a time lapse thing. That's basically all I had for today. Thank you so much.
Thank you very much. Thank you all. Very exciting. So now we still have time. I got information that we can go a bit over time for discussion. So we still have time for some discussions. So if in the audience, anyone had a question, just raise your hand or use the QA. While we're waiting for question, I would just allow Yakomo to quickly summarize his point because we already saw it on the slide, but maybe just quickly summarize your 3 key points that you had, and then we'll kick off the discussion, if you don't mind.
Yeah. So thank you very much for saying. I mean, I think the key point that I was trying to make, and I mean, in line with a number of the other points that were made, and even harking back to Clark's talk, we're increasingly seeing the right way in which to build safe and secure and correct ML systems by having a lot of the implementation complexity move into artifacts that sit outside of a specific model pipeline. And so this is really what we mean by tooling and platform enablement for how we think about designing, building, and deploying machine learning in the real world. And it's happening, as I mentioned before, it's happening everywhere, for a broad category of data science applications, many different techniques. I mentioned the NVIDIA Merlin framework for recommender systems, of which there are many. We're seeing more and more deep learning frameworks, even for tabular data, in ways that are substantially changing how we think about building models on top of tabular data, of which TabNet that I mentioned before is one. But we're also seeing even I think I can send on the chat to attendees like something like reinforcement learning as a service, right? Even black box optimization, like think of VZA available as a service on GCP. We have explainability increasingly like available as a service. And again, these are just exemplars, but they are in a way ripping out a lot of the technical complexity that would otherwise have to be navigated by every single development team looking to develop that next model. And so Futsa, to your question before, I don't know that this is certainly not making things foolproof. We need people who understand what they're implementing and understand all of the things that can go awry, but just making, let's say, the surface area of complexity that people have to navigate, reducing the size of code footprints, I think starts to introduce some of the safeguards that we need in order to be able to do this well and to build ever more robust systems. And again, the main thing that we're seeing here is increasingly, one of the ways in which we're seeing more and more of ML make its way into the real world is by becoming more and more integrated into, what are otherwise other kinds of software systems, right? So ML is just a specific, a technique and set of tools by which we can get at specific features and functionality within that software. I'll pause there.
Okay, thank you. Thank you very much. So while we are waiting question for the audience, maybe I will kickstart our discussion. I want to come back to one of the recurring themes across all the pitches, which is the safety. Right? So it turned out we're trying to build complex systems, sensitive system with a quite brittle technology. Right? And we need to reach safety. And somehow currently we're using engineering to try to compensate for the limitation that we may be having around the technology. So my question for you is, do you think we can achieve a level of acceptable level of safety just by engineering, tooling around the machine learning pipeline? Or we need to maybe go back to the way we are learning as well and try to do something there? Like what do you think about it? Why do you think we should be putting much of the effort here if we want to achieve this goal of safe AI that could be safely released to users? We want to go first. Maybe Mario Masinse? You mute.
Okay, I think my position is that for the first one, which is I think that within the current technology, machine learning technologies, still we can have enough engineering discipline that makes the machine learning, usable for the real world applications. And the reason is that the George Box statistician said that every model is wrong, but some models are useful. And I think it is very important for us to identify these useful models instead of trying to create the complete models. So that's my position.
Okay. Anyone else?
Yeah, if I could chime in, I mean, I think in control systems, we view like performance and robustness as two orthogonal objectives, right? And there's no, I think the case is, pretty much closed that for a lot of these systems, you're just, in terms of performance, there's just no way you're going to beat these like deep learning based models. So it's incumbent upon us to build either, the infrastructure around it or the actual tools within the learning mechanism itself to explicitly to provide the signals for us that we need in order to build in robustness. So I've kind of dodged your question because I think there's the two paths that you outline are kind of the two main options, right? But again, I go back to this notion of intrinsic measures of uncertainty and the work that we're doing on out of distribution. It really seems to me like those kind of tools, if we can make breakthroughs in those kind of tools, that will be a key enabler to getting these systems out into the real world. All you need is the model to be able to tell you when it's not sure.
Yeah.
And then you're good, right?
You can compensate with.
Exactly. Then you can build the engineering infrastructure around it in order to do whatever you need to do.
Other opinions?
Yep. My take on it is that you still need the engineering guardrails either way, right? So even if you have let's assume hypothetically perfect, model or system. I mean, if you think of human level performance, humans make a lot of mistakes, and we still have these systems in kind of controlling the bounds of what they can make. I think the problem is what kind of mistake you're going to make and what application or what domain you're in. So in domains let's say surgical robots or domains where you have a legal system or health system, you have to be scrutinizing the system even more and have a lot of these guardrails at each and every layer. So it's defense in depth versus in another system where you're making recommendations for, I don't know, music recommendations. The bar is much, much lower, and maybe you can rely on improvement in learning, where you have error minimization to a level where you can say, well, there's some leeway here. But I think either way, you want to be careful about dropping one versus the other. I think it's required but insufficient.
Okay, interesting. I agree. Any other contribution around this? Then my next question to you is, from your perspective, beside the safety will appear to be the obvious bigger challenge that we're facing here if we want to release product. What do you think, from a researcher point of view, like this community, we have a lot of people doing research around this engineering of ML systems, so they're trying to contribute with new efficient techniques, new ways to engineer those systems, improve their quality. What would you say is the number one area where people should be looking at, which is, to your perspective, still underexplored?
I don't know. I mean, maybe, very quick thought. I think, as Mohammed was also saying, when we were talking about like maybe the plethora of tools that, we have available for regular software development, and, as much as the ecosystem is growing and, we maybe have the right conditions now, both at the level of underpinning layers, and infrastructure, things on the cloud, things like Kubernetes, that will help grow the ecosystem out. There's a lot of open problems and challenges, right? And I think there are a number of open research problems, but also, there will be, in order for a specific technique to be usable for a model development team, it needs to make its way all the way into, hardened industrialized technology, that hardened component that can be deployed, right? So we're, and for that matter, maybe a lot of the problems that we've been talking about is just at the level of, a lot of data science still uses things that are, papers that have been it's specific techniques that have been adapted from papers, right? And the code associated with those papers. So, which again is far from a hardened implementation. I mean, we've seen, just like Quantum Black, like some of the problematics around doing that, right? Like in the context of some of the work that we've been doing in time series forecast and using, in collaboration with Element AI, like trying to adapt something around NBeats, which was, their specific framework for, time series forecasting, developed around the M4 data set and, a specific publication, but trying to take it into a number of other contexts and seeing a lot of the heavy lifting and, a lot of the engineering problematics and hurdles that have to be navigated in taking that implementation and generalizing it and making it fit for purpose to sit in a production environment. But I would, if I were to call out, two specific challenges. I mean, one, I think there's maybe, Futsi, going back to your point about the underspecification of ML. I think there's need to move into to have much more, let's say, a rigorous underpinning and more, platform enablement around how we run experiments, right? As much as we look at historical performance on the one hand, I think a lot of data science, and for any number of reasons, including around confounds and omitted variable bias, any number of structural points, we want to be able to get to, deployed models where we are looking at the performance of the models, seeing how they behave, perhaps correcting for structural deficiencies on the back of the data that we're collecting post deployment, live. But it means that we're much more rigorous about how we A/B test models and how we baseline them. I think a lot of, and I think, there's a number of different tools and frameworks and components. Again, I would call out Determined AI and their model registry components as things that are moving us in the direction of, improving repeatability around data science, which is great. All of that said, in too many different situations, at least, you know, the ones that we see in a lot of different, you know, organizations and work that we do, there is too much bespoke code that has to be written around how do I baseline and benchmark a model, and how do I run experiments to be able to look at how, you know, if only at the level of hyperparameters, how a specific change in those hyperparameters is affecting performance. Yeah.
Change impact analysis and the others. We definitely need more tools.
Yeah, I completely agree with everything that Yakima just said. Like, I think like the tools of, even just like the tools of containerization for us in robotics have been pretty transformative, right? Because now we can ship software and, you know, have a much higher degree of like expectation that on the other end it's going to work without, you know, someone having to like disentangle apt-get confusion for 18 hours or whatever. And that's already been like, that's the huge enabler for us of the whole AI driving Olympics thing, right? Everything is shipped around as Docker images. And that is, so yeah, the notion that at the very least we like hold ourselves to a little bit of a higher standard in terms of what we call science. And I think we're like, it's really moving in the right direction. But there was a period there when the like when there was a lot of papers that were coming out that were like junk science, like not real science, like not evaluated properly. And I think that as a community, like, I mean, as a research community, as an academic community, this could be one of our roles, you know, where we stand there and say, hey, wait a second, like there's a proper way to do scientific experiments in order to like justify your conclusions, and you know, you haven't met the bar or whatever.
I want to add up a few points. Actually, I agree with Yakimo and Liam, specifically what you mentioned earlier on understanding uncertainty. Like neural networks, deep neural networks specifically are really bad at this. They could be extremely sure of, you know, making a decision, but it's the wrong decision. And if you can anthropomorphize that and think of like, if you have a human or an assistant who's very sure, but they're really wrong, it kind of breaks the trust. And I think trust is extremely important in human-computer interaction, specifically when you're talking about non-deterministic systems. So I think there are two facets to this. The first one is how to reproduce results in terms of like whether you're building on top of somebody else's work, especially now with the explosion of like a lot of pre-trained models, and how can you basically have trust in that implementation, because you're kind of borrowing a lot of logic units into your software, right? Before it used to be libraries that you can unit test and verify, but now these are building blocks of somebody else's models that you're introducing into your ecosystem, into your own solution. The second one is actually more about the under specification of like AI products or solutions. One of the biggest challenges, I think, especially from the industry perspective, when you're talking to customers and clients, they think of solutions just the traditional way, software 1.0. You open up Word, you expect it to work. You check grammar, it just works. You can replace the words. You change the font, it just changes, right? There's some sort of trust in the system just works. And when you're communicating to them expectations about AI, a lot of the times people look at AI solutions as the traditional software. It should just work 100% of the time. Like, why wouldn't it, right? There's no messaging that says, by the way, this probably will work, right? It always like, here's the AI solution that will solve this problem. I think language is very important and expectation management is very important. And this goes all the way back to like specifying what is it that you're trying to solve. You're trying to solve a problem. You're not just 100% communicating that it's going to work. This is, I think, the trustworthy computing that has been, you know, a very important goal for the industry. And we've worked collectively so hard to establish like your trust in putting mail in the cloud, your trust in banking online. Now we have to think about like trust in working with AI.
That's a very interesting, very good point, actually. It's often overlooked, things we're doing. That's very...
Yeah, if I can chime in on that, I also really agree with that, and I think that's an excellent point. When it comes to like human-machine interaction, I think we should always keep in mind that there's like two options. We can like make the machine really good, or we can educate the human to expect like and mitigate their expectations. And if you take the autonomous car as an example, the successful, by and large, the successful like autonomous car deployments are like these shuttles that move really slowly, and nobody like expects like them to do anything crazy. They don't expect them to behave like people. They understand their operation. It's like there's a contract between the people and the system. The people accept the system as being like suboptimal, but they are happy to trade suboptimal for like repeatable or like predictable or whatever. And so there's like on the like multi-objective optimization of all these systems, there's so many different factors that can all be considered. And the application that you're in, you might need to consider these different factors and weigh them differently, right?
Yeah, definitely. Maybe one last point from the panel. Marima Sensei, you want to chime in?
So I completely agree that the expectation control is very important, and I think that is related to the requirement development. So how you get the requirement from the customer, and the customer usually don't know what they really want. Okay, and for example, if you are talking about the self-driving car, of course, safety is important. But if you want to have 100% safe car, then the car doesn't move, right? Because right. So the customer has to be explicit that what kind of risks about the safety I can get, right, is in the cost of the, get the benefit of the moving cars. So I think it's very important to have more, discipline in requirement development, and we can get some help from the software engineering community.
Yeah, definitely. I think our colleagues in the requirement engineering have a lot to contribute in this space. I think we are way over our time, so it was so very interesting. Couldn't control for the time. I think I got the okay from Kaz to go a bit over time, so I think we're good. Unless there is any specific last question from the audience, I will thank you, everyone. Thank you very much for the very lively discussion. Thank you for all the inputs. And I will pass the baton to Kaz. Kaz?
Thank you for great discussion for panelists. And I want to end this discussion, but I have one quick announcement. Next session will start at 1 p.m. UTC for research talks and a poster session. So see you again. And thank you all.
Thank you very much. Thank you.
Thank you.
Thank you.